Hey everyone, welcome back to AP Precalc. This is lesson 3.8. Let's get right into it. All right, so bell ringers are going to be looking a little different from here on out. We are already towards that home stretch of the school year, and so we are going to start our exam prep now. For the multiple choice section, you are going to have your bell ringer be 3 multiple choice questions. I'll give you around 5 minutes for this, so it's going to be a little bit longer than your average bell ringer, but still very, very important. This is going to prepare you for the multiple choice section. I will collect this at the end of the school year, so during your semester summative for a 20-point grade. So it's going to be worth double what regular bell ringers are worth. So very important. And I will not have a lot of extra copies because the packets are so big and long to print out. So please make sure to bring it every day. If you aren't here for a day, you are still expected to complete the 3-peats for that day. All right, so pause the video if you haven't done this first 3-peat yet, because I am about to go over the answer. So for number 1, we have a table of k that shows values at selected values of x. Which of the following claim and explanation statements best fit this data? And so here we're given 2 options. It's either linear or quadratic, and then with an explanation. So let's first identify whether it's linear or quadratic. So first, let's find the rates of change or average rates of change by looking at the first difference of each of these. Here we see +1, we see -1, -3, -5. So we see that our average rate of change or first difference is not constant, right? They're not the same. And this is over equally spaced inputs. So here they're all +1, +1, +1, +1, which is kind of a given for both linear quadratic, but it is important just to note that. But here the first differences are not constant, so we know it is not a linear function because of that. So we can eliminate A and B. Taking a look at the second difference, here we see -2, -2, -2. This is the second difference. Or we can say the change in the average rates of change. That's how we can also describe these numbers here, which they are all constant. They're all the same. And so let's take a look at the explanations for C and D and see which one best models a quadratic function. So for C, because the rates of change over consecutive equal length input value intervals is constant, that's just saying that this is constant, which is not true. So we can kind of eliminate C from that. Let's take a look at D though, just to make sure. Here it's quadratic, that's good, because the change in the average rates of change, this is the second difference over consecutive equal length input value intervals, that's a given, is constant. So the second difference is constant is what it's really trying to say, which is true, right? These are all the same number. So D is our correct answer for number 1. Number 2, let G of n represent a geometric sequence where the third term is 8 and the fifth term is 2. What is G of 8? What is the 8th term here? So taking a look, what I would do is I would use our formula. So remember, G of n equals G of k times r to the power of n minus k. In this case, remember, G of n is going to be your later term and G of k is going to be your earlier term, and r is going to be your common ratio. We have 2 terms, but we don't know what our common ratio is, so let's solve for that first. I'm going to set this as my G of n, and then the third term will be my G of k. Here, then, we should get 2 equals 8 times r, we don't know that yet, and then n is that small subscript, so n is 5 while k is 3. This then should be 2 equals 8 times r squared. Solving this equation for r, I'm going to divide both sides by 8 to get 1/4 equals r squared. Take the square root of both sides to get r equals 1/2. We can assume r is going to be positive in this case, not negative 1/2. So now that we know our common ratio is 1/2, we can now use that to find G of 8. So G of 8 is going to be equal to If we use our formula again, g of n equals g of k times r to the power of n minus k. G of 8 can kind of be our g of n, and then g of k, we can just reuse this, that's fine. Or we can reuse this one. Either one should be the same. So let's do g of k is going to be g of 5, which is equal to 2. So this is going to be 2 times r, which is 1/2, to the power of 8 minus 5k. That should be a minus. So then g of 8 equals 2 times 1/2 cubed, which is 2 times 1 over 2 cubed is 8. 2 over 8 is 1 over 4. And so that should be our answer, C, for number 2. And then number 3, the figure shows a circle centered at the origin with theta in standard position. What is the value of sine theta, knowing that this is the radius is 13, and then this coordinate here is 12 and 5. However, theta is not going to point P, it is going to point S. So we are gonna want to use that as our triangle. So remember, we have to use one side has to be with the x-axis, one side has to be with the radius, and then the other side has to form that right angle. So our triangle we're going to want to extract, let me enlarge that a little bit, should look like this, where this is theta, this is our right angle. We have 12, we have 13 as our radius, but then this is -5 because you're going down this time. So be careful of that. And then we want sine of theta, which is opposite. So -5 over hypotenuse, 13. And that should just give us D with that negative sign out in front as well as the correct answer for number 3. All right, so remember from the last unit, we first introduced tangent of an angle in topic 3.2. There's a few definitions for tangent, right? Tangent is, so if we have tangent theta, this is equal to sine theta over cosine theta. This was also equal to the slope of the line. So if the slope of the line is 1, then tangent theta equals 1. So a lot of different things. We're going to revisit that today because today is talking all about tangent. So here, like I just said, tangent is equal to sine over cosine. Tangent is also just equal to the slope of that line if it was just y equals mx, or it's equal to opposite over adjacent. If we extract our triangle using SOHCAHTOA, it's going to be our y over our x there. All right, so like we previously did with sine and cosine, I want to use what we know about tangent to kind of build out its graph. And so let's take a look at the tangent of the theta, or an angle, when it goes from 0 to pi over 2 radians. And so remember, tangent is just the slope of the terminal ray. So let's start by almost like guesstimating the slopes here for each of those 5 circles there. So this first circle, when theta is 0 and it's a flat line, the slope of a flat line is just going to be 0. So we know that, pretty easy. This next one here, it's kind of hard to tell what theta is. These are just guesstimations, so the actual numerical values that I'm about to spit out are not important. What is important is understanding how they relate to one another and how they change as you go from 0 to 90 degrees. So this one, I'm just going to guesstimate is like 1/2 maybe. Here, this kind of looks like, it's a nice slope of 1. And so I'm going to guesstimate that as 1. Here, this is getting a little bit steeper. So maybe 3 there. You could make the case for 2 or 4. It doesn't matter. As long as it's getting bigger or a bigger number than 1, that's what I want to get at. This one here, this is getting really, really steep, right? It's going to be a pretty big number. Let's go like something like 20 here, right? So when theta equals 0, when it's at 0 degrees, you start at a tangent, you have a tangent value of 0. And then as theta goes from 0 to 90 degrees, or pi over 2 radians, you're going to get bigger and bigger and bigger. And ultimately, when you get super, super close to this line, right? If it's like something just like that, the slope could get really big. It could get like 100 or maybe even 1,000 or 100,000, right? There's no restrictions on how steep that line can get because it's almost going to become a vertical line. And that's what's going to happen when it hits exactly 90 degrees. It will become a straight up vertical line like that. And now, what is the slope of the vertical line? Well, remember from Algebra 1 or Algebra 2, the slope of a vertical line is technically undefined. And this is important because with this, we can now say tangent of pi over 2, because the slope is undefined, tangent of pi over 2 is undefined as well. So tangent of pi over 2 is undefined. That is something that's really going to be important as we build out our graph later on. Now that we know it's undefined, right, as we approach that from the left-hand side, we will be going to positive infinity. So for example, let's take a look. Let me redraw this here. Um, if we kind of sketch out the graph, right, as we go from 0 to pi over 2, you're going to start at 0, and then this is going to go up and up and up, but at pi over 2, it's going to be undefined, so that's going to be infinity. We'll put all these pieces together and look at the entire graph of tangent in just like a few minutes, so just bear with me here. But now let's see what happens as we go from pi over 2 to pi. So let's play this guesstimation of the slope game again. So here, when it's like this, it's really steep, but in the negative direction. So this might be maybe around negative, like, we'll go negative 20 again, right? A really steep slope. This one's not as steep, but still a little steep. We'll say maybe negative 3. Here, this looks pretty good, like a perfect 45-degree angle almost. And so this, I'm going to say, has a slope of negative 1 as like a guesstimation. This slope right here, still negative, but less than 1, so, or greater than 1, so negative 1/2 would be a good slope there. And then at exactly pi, or 180 degrees, it's flat, so we do know that that is going to be 0. So from pi over 2 to pi, right, if we almost continue this graph, we actually are going to start at negative infinity, and we're going to make our way up to 0. So that's going to be what that first part of tangent looks like, and I'll get to that later. All right, one more time, let's do this. Let's look at it from pi to 3 pi over 2. And so here, the slopes become positive again, right? It's a small positive slope. So if we guesstimate it, maybe positive 1/2, right? That might be a good slope. Here, this looks maybe like, let's say negative, that's hard to tell, maybe negative 1. And then this looks maybe a little steeper, so maybe negative, or positive 2, sorry, and positive 1. These are all positive slopes, not negative. This one's getting pretty steep, so maybe 20, like positive 20. And then this one is exactly at 3 pi over 2, right? It's again a straight up line, and so this one's going to be undefined there at exactly 3 pi over 2. Right, so there's a few key concepts that I want to get at here. Every time the terminal ray is vertical, the slope is undefined, which means tangent is going to be undefined at those values as well. When we approach that, from the left-hand side, we're always going to be approaching positive infinity, and then from the right-hand side, you will always be approaching negative infinity for tangent. That will always be the case. That's kind of what we saw, right? As you're going up to pi over 2 from 0, you're getting steeper and steeper in the positive direction, and then as soon as you go past pi over 2, you turn negative and are getting less and less steep from the negative direction. We also know that when we graph the tangent function, because it's undefined there, it is going to be vertical asymptotes at pi over 2 or 3 pi over 2. And this is not just the case, right? However, if we have this at pi over 2, right, it's a straight line vertical asymptote. If we add pi 180 degrees at 3 pi over 2, it's a straight line vertical asymptote. We keep going. At 5 pi over 2, straight line, vertical asymptote. 7 pi over 2, straight line, vertical asymptote. So then how do we encompass all of these vertical asymptotes if I said, give me every vertical asymptote of this equation here, right? How do we encompass all those? And it's done by x equals pi over 2 plus pi k, where k is going to be an integer in this case. And this equation encompasses every single possible vertical asymptote. So where you start at pi over 2, and then you add or subtract nice whole multiples of pi radians or 180 degrees. So this is the graph of tangent. This is what it looks like. I would commit this to memory. Very, very important. But let's break down a few key characteristics about this graph that I want to hit. The first one is it starts at 0, 0. That's going to be kind of like the tangent starting point, kind of like how sine is starts at the midline going up. Tangent starts right at the middle, and then you can either draw it from either direction. As you go from 0 to pi over 2, like we saw, at pi over 4, it's exactly 1, and then you just keep getting steeper and steeper. And then at pi over 2, right, we have a vertical asymptote. That's because it's undefined. Then you start at negative infinity, and as you approach pi, you're going to get closer and closer to 0. And then as we saw from pi to 3 pi over 2, you are going to go back up to positive infinity and have another vertical asymptote there. Because this function is periodic, it is going to be the same thing, but copy and pasted. So it's like almost as if you take this and you copy and paste it. Boom, copy and paste it. Boom, there you go. Knowing that, what is the period of tangent? Well, we know our asymptote equation is going to be x equals pi over 2 plus pi k. This is actually going to be our period as well. So every pi is when it repeats itself. So here you'll have pi. So from negative pi over 2 to pi over 2, that is a distance of pi. And then it repeats itself from pi over 2 to 3 pi over 2. That has a distance of pi. This has a distance of pi as well. And so that is the period of tangent is pi. All right, so this is important features on the graph of the tangent function. This general setup or equation is very similar to sine or cosine, just with the word tangent instead of sine or cosine. The first thing is vertical dilation of the graph of tangent by a factor of a. You will not need to worry about this. The main thing you will need to know is if you have, let's say, y equals a tan x, right? If a is positive, the graph of tangent should look like this. Pretty simple, right? If a is negative, the graph of tangent should be the same, but reflected. So it should still look like that, look like that, look like that. So that is what you'll need to know, whether a is positive or negative. How does that impact the shape of tangent, right? And I just remember it right. Positive, this has a positive slope, it's going up. Negative, this has a negative slope, it's going down as you go from left to right. The next thing is your period. So typically from sine and cosine, we learned your b value was 2 pi over your period. And that only works for sine and cosine, right? It does not work for tangent. So here, when we're talking about tangent, we're going to almost erase that equation from our mind. It is useless. So let's get rid of that. And let's write a new b value equation. And I want to specify our tangent b value is going to be pi over the period. Right? That's how we find the b value. And they just did the same equation, but they swapped the b value and the period, which you can always do with fractions. And so, for example, let's say I have the period of, let's go 3 pi. Then my tangent b value would be pi over 3 pi, which means 1/3 should be my tangent b value, not 2/3, which would be what you do if you do 2 pi over 3 pi, right? The next thing is phase shift. This is the same as like sine or cosine, right? You're moving it to the left. It's going to be minus c units. So just be aware that it's going to look like the opposite of what it should do because it's a horizontal translation. And then vertical translation is going to be straightforward on the outside. So move the graph up or down by d units. And that you can usually tell by that point of inflection is typically on the regular tangent graph is found at 0, but let's say you have a new graph. Let me do it in blue, right? Where you have that point of inflection up 2. Your d value there, if we know this is 2, is going to be 2 because this moved up 2 units at some point. All right, so let's work through a few examples. Example 1, a portion of the function f is shown above. Find a, b, and d. Assume a equals 1, so here, don't have to worry about that. It will be the same way on a test. Now let's find our b value. And so here, let's look at our period. Well, I look at vertical asymptotes for tangent. That's how I find the period. You can find it a few different ways, but I like vertical asymptotes. We're going from negative pi over 4 there to positive pi over 4. This is not a length or distance of pi over 4. It's a length or distance of twice that, which is going to be pi over 2. So that is our period. Our period here is pi over 2. And so our b value should be pi over 2, which is pi times the reciprocal. So keep, change, flip, which is just 2. So here b should be 2. Our d value, here we see the point of inflection falls at the x-axis when it is 0. So this graph has not been shifted up. So d is going to be 0 in this case here. Example number 2. The function h is defined by 4 tangent 2x plus 5. What is the period? So here we have our tangent b value of 2. So then our period is simply going to be pi over our b value. Not 2 pi, but just pi. So that is actually our period. It's just pi over 2. Here, example number 3. What of the following gives the vertical asymptotes to the graph of g? So here, there's a really easy trick. The long way is just by graphing it by hand and looking for the vertical asymptotes. That takes a lot of work, and so a quicker way is by memorizing where does just the graph of y equals tangent x have vertical asymptotes? Well, I know that's at pi over 2 plus pi k. And now I want to see how does this change in terms of its period. Well, the a value and the d value really don't affect, the vertical asymptotes, which are based on your x values. And so the only thing that's going to be affected is that 1/3 x that's on the inside of the parentheses. And now I think of this as like, what does this do to the graph, right? What does this do to the period? Well, here our period is pi, just for regular tangent. Now thinking about it now, when you have 1/3 x on the inside of the parentheses, your b value is 1/3, which means pi over your b value should give you your period. This means your period is now 3 pi. And so we're stretching our period out by 3, right? We multiplied our period by 3. So that means to find our asymptote equation, we can multiply everything in here by 3. So pi over 2 times 3 is 3 pi over 2. So this times 3, and then this times 3, and that times 3, and then plus not pi k, but 3 pi k. And this is our new asymptote equation. This should match up with C, so C should be the correct answer there. So that is going to be a really quick way to do this. I would recommend doing that because you'll see a question like that probably show up on a test or a quiz. All right, example number 4. The portion of the function k is shown above. which of the following could be the expression for k? So here, let's take a look at what we see. Well, first I see that point of inflection, right, is at -2. So -2 should be our d value. So we can eliminate b and we can eliminate d just from that. And now I want to look at what is our period, because the only thing that changes is our b value. So our period goes from -pi to pi. So our period is going to be 2 pi, which means our b value should be 1/2. So that's the number we should see on the inside, making A the correct answer, not 2 or C. So A is the correct answer for example number 4. All right, example number 5. Graph tangent x over 2 plus 1. So let's do that now. Let's see how this impacts the graph. So first, I'm just going to graph the graph of tangent. You will never be asked to graph anything on the AP exam, but it is important to just know how to graph functions. So here I know there's zeros at 0, pi, -pi, even 2 pi, and -2 pi. And then the graph of tangent looks like this. So let me draw that. This is just the graph of tangent. Now let's take a look at what happens here. Our b value is now 1/2, which means pi over 1/2 is 2 pi. That's going to be our period. So our period is no longer pi. Our period is now 2 pi. So we have to stretch this graph out by 2. So let me redo that now and redraw these lines. So knowing that our period is 2 pi is huge, and so that completely changes our entire graph of tangent. So what we are going to do now is I'm going to make a vertical asymptote pi units away this way, pi units away this way, right? And then this is going to be my graph of tangent, like that. However, and then at pi over 2, this should go through 1, and then at -pi over 2, this should go through -1. So those points should be hit in the graph of tangent. So let me redraw this equation again. Something like that, right? And then the final step is that plus 1. So let's take care of that by just moving every point that we have up 1. That will not impact our x values in any way. And so this should be our new graph there. And let me erase all the red stuff so you don't get confused. The purple is what matters. So that is our graph or our answer to example number 5. All right, now tangent on the unit circle. Remember, tangent is just simply sine over cosine. So to find tangent of any angle, just take sine of that angle divided by cosine of that angle. So filling in this chart for any angle between 0 and 90 degrees, sine is, remember, 0, 1/2, root 2 over 2, root 3 over 2, 1, and then you flip it. And then sine or tangent is just sine over cosine. So this is going to be sine over, so 0 over 1 is just 0. Here you have sine, which is 1/2, over cosine, which is root 3 over 2. This becomes then 1/2 times 2 over root 3, which really just becomes 1 over root 3. So let me erase this and just simplify that. Here, this becomes root 2 over 2 over root 2 over 2. This just becomes 1 because they're the same number. And then here, this is root 3 over 2 over 1/2, which is equal to root 3 over 2 times 2 over 1. Those will cancel out, and we are just left with root 3 there. And then tangent of 90, or remember this is pi over 2, is just going to be undefined, just because cosine is going to be 0 at that angle there. Right, so now that we have that, we can fill in some of the other stuff, like the values using the unit circle. So using the chart that we just did, let me fill in the first 3, right? Tangent of 30 degrees is just 1 over root 3. No need to rationalize the denominator, but if you did, you could have root 3 over 3. That would be fine too. Tangent pi over 4 is just 1. Tangent pi over 3 is root 3. And now filling in the rest of these, it's going to be the same. Just remember to use reference angles and add negative signs in the second and fourth quadrant, right? In quadrants where tangent is negative. So this should be negative 1 over root 3. I'm going to give you the rest of these answers here. You can look them up on your unit circle. Whoops. Root 3, negative 1. This is undefined. Tangent pi is 0. This is also undefined. Right, so that is our answers to example number 7. If you have any questions, please come see me in office hours, and I will see you guys later. Thanks.